Okay, weak acid, strong base titration. Moving on to part B. Right, so same weak acid we started with, but now part B, we've started to progress through the titration. We've added 10 mils of sodium hydroxide. So what we need to consider here is, first off, the reaction between our weak acid and this strong base that we've added, right? And then we're going to have to take into account the equilibrium that will be present between the weak acid and its conjugate base. So couple equations, common ion going on here, and this particular solution will be a buffer. We'll see how that relates to how we solve the problem as well. But first, let's start with this reaction between the weak acid and the strong base. So I'm just going to use HA again for the weak acid. It's going to react with sodium hydroxide. Since that's a strong base, this will be a one-way reaction. Right? And that's a hydroxide base, so it'll produce water. Right? And in this case, the sodium is going to be left over, and I'm going to keep it separate, sodium cations. Right? And then we'll also get the conjugate base here. The strong base is going to deprotonate the weak acid, and it's going to produce some of the weak acid in solution. Now, since this is a one-way reaction, we don't really need to think about the ice chart. It'll be more appropriate to think about the if chart and use moles of each component. So we need to figure out now, right, it wasn't relevant for part A, but is now, how many moles of weak acid do we have? How many moles of this strong base did we add to our solution? So taking the volume and the concentration of the weak acid that we had at the beginning of the problem, if I take 40 milliliters of my weak acid, its molarity is 0.25, so there's 0.25 moles in every liter. And again, I'll change that directly to 1,000 milliliters to save a step here in the calculation. If I multiply that out, 40 times 0.25 divided by 1,000, that's 0.0100 moles of my weak acid. So I'm starting with 0.1 moles of weak acid. Now that was my acid. I want to do the same for my base, which is my sodium hydroxide. Now for part B, it's 10 mils. We've added 10 milliliters of NaOH. The concentration is the same as it was for the acid, so 0.25 moles per liter. Again, I'm going to change that to 1,000 milliliters, right? And that would work out to 0.0025 moles of sodium hydroxide. So 0.0025. Okay. Now, so they're not the same. So this is essentially a limiting reactant case. We've got excess acid. We don't have as much base, so the sodium hydroxide is our limiting reactant. So how much of the limiting reactant we have is going to determine how much of the product we get. Now, we're not really concerned about the water. That's not going to change our overall volume. We're not concerned about the sodium because that doesn't change pH, right? But we are going to get 0.0025 moles of our conjugate base, right? And if 0.0025 moles of acid react with, or base react with this quantity of acid, then we're only going to have 0.0075 moles of our acid left after this first reaction has taken place, right? And now we're going to have to factor these into our equilibrium. Now, the equilibrium from there is the same as we had for the first problem. Our benzoic acid, weak acid, is going to react with the water. It's going to protonate it to make hydronium ions, and that's going to result in the formation of the conjugate base, benzoate here, A-. Now, because this is a buffer, right? We said a buffer is a weak acid and its conjugate base in solution, right? There's kind of a shortcut, or again, a way we can simplify this particular problem. So generally what we would do here is take our equilibrium constant. Sorry, that should be a 3, H3O plus times A- over HA, right? And we would solve for the hydronium ion concentration. Because this is a buffer, and because we have both a significant concentration of the weak acid and its conjugate base in this solution, what we can do if it's a buffer, and let me make sure I write that down here, you can only do this for a buffer solution. We couldn't do this for part A, or we'll see in a part coming where there's just base. We can separate the right side of this equation. So we could separate out hydronium. Now this you could do for any equation because this hasn't changed anything yet. Right? But if we separate out that ratio, when the solution is a buffer, the ratio of the concentrations is the same as the ratio of how many moles of each are present, since this is one solution and both of these are in the same value. So when we're looking at a buffer, we can do this. We keep concentration of hydronium, but that ratio, the conjugate base to the weak acid, we're going to change to moles, because the ratio of those concentrations is going to be the same as the ratio of how many moles of each are present. We just figured that out up here for the one-way reacid with the strong base. So from this equation, if we just plug in, right, we know Ka, right, hydronium ion concentration is what we're trying to solve for, so I'll call that X. Right, moles of the conjugate base here is going to be 0.0025. Moles of the weak acid is 0.0075, right? And now I have an equation where I just need to do a little manipulation to solve for X, right? So take 6.35 times 10 to the minus fifth, multiply by 0.0075, divide by 0.0025, right? So net result there is multiply by 3, 1.89 times 10 to the minus fourth molar. That is going to be the concentration of hydronium ions in this solution. Right, so I take the negative log of that to get the pH, and the pH here is 3.7. Right, and again, we should compare that to part A. We started out at 2.4. We've added some strong base. The pH went up. That makes perfect sense. It went up just a little bit. That makes sense too, because a buffer helps moderate how much the pH is going to change, right? So if we can recognize the solution we're looking at as a buffer, we can make this simplification, and that's going to make it a little bit easier to solve the problem. But be careful. Don't try to do that if you're not in a situation where we have a buffer, right? So we'll have to do this analysis to make sure we have both the weak acid and the conjugate base in solution to be able to do this. Now, we'll go on to the next page and the next part of the problem.